All right, get ready for a deep dive straight into the core of Python. You know how you're always looking for that shortcut to becoming well-informed? Well, today we're going to dissect two really concise summaries. They promise to reveal Python's deepest secrets. Get ready for some serious ha-ha moments, because we're going to uncover why Python treats everything as an object. I mean, everything from simple numbers to entire modules. It's kind of crazy. Plus, we'll crack the case of Python's dynamic typing. It's almost like a detective story where the variables change their identity on the fly.
It's definitely all about understanding both the elegance and the quirks that make Python so powerful. Let's break it down.
Both sources make a bold claim right away. Everything in Python is an object. Yeah, I get that. Numbers, strings, lists, those are objects. But functions and modules, too. That's kind of mind-blowing.
Think of it like this. Imagine building something amazing with Legos. Each block, no matter its shape or color, is a fundamental unit, right? Well, in Python, everything is like those Lego blocks objects that can be combined in countless ways. That's a big part of what makes Python so incredibly flexible. You can build anything from simple scripts to complex web applications, all using the same building blocks.
Okay, so I'm seeing the Lego analogy. But how does treating everything as an object actually make our code better?
Well, for starters, it promotes something called code reusability. Let's say you've created a function to sort a list of numbers. Because it's an object, you can reuse that same function to sort a list of names, or even a list of more complex objects like customer data. You don't have to reinvent the wheel every time you need to do something similar. Plus, this object-oriented approach lets you build complex data structures like trees or graphs by combining simpler objects. It's really like building a skyscraper out of those Lego blocks.
That's a great point about reusability. I hate repeating myself, in code or in life. But here's where I always trip up. Python's dynamic typing. I'm used to languages where you have to declare a variable's type up front. In Python, it's like the Wild West.
That's one way to put it. Python doesn't require you to specify whether a variable is an integer, a string, or whatever. The beauty of it is that variables simply act as references to objects. The object itself carries its type, and the variable just points to it. It's like a chameleon adapting to its surroundings.
So the variable's like a label that can be attached to any type of object. That seems super flexible, but doesn't it lead to chaos?
It definitely can if you're not careful. Experienced Python developers use a technique called duck typing. It's like saying, if it walks like a duck and quacks like a duck, it's probably a duck. We care more about what the object can do rather than its specific type.
I'm starting to see the elegance, but I can also see how that could lead to some nasty bugs if you're not paying attention.
Exactly. That's why even with dynamic typing, Python developers are increasingly using type hinting. It's like leaving little notes in the code to make the intended types clearer, which helps to prevent those gotcha moments.
Type hinting sounds like a good compromise. You get the flexibility of dynamic typing, but with a safety net. Okay, let's move on to how Python handles functions and their arguments. I read that it does something called PI reference. But honestly, that always goes over my head.
It's a concept that trips up a lot of people. But think of it this way. Imagine you want to show a friend a funny video online. You could send them the entire video file, which could take ages to download, or you could simply send them a link to the video.
Ah, so the link is like a reference, pointing to the actual video without making a copy.
Exactly. That's what Python does when you pass an object as an argument to a function. Instead of creating a whole new copy of the object, which could be memory intensive, it passes a reference, a pointer, to the original object's location in memory. This makes things much more efficient, especially when dealing with large data structures.
Okay, I'm starting to see how this reference thing works. But if a function modifies the object based on the reference, does that change the original object too?
That's an excellent question. And it brings us to the concept of mutable versus immutable objects. Hold that thought, because we'll unravel that mystery and dive into the fascinating world of namespaces. In the next part of our deep dive, stay tuned.
Welcome back to our Python deep dive. Before we got sidetracked by references and videos, we were talking about how Python passes arguments to functions. You left me hanging with this cliffhanger about mutable versus immutable objects. It sounds kind of ominous, like some objects are destined to change and others are forever frozen.
Yeah, it's not quite that dramatic, but the distinction is definitely important. Think of it this way. Some things in life are easy to change, like a playlist on your phone. You can add or remove songs, whatever you want. But other things are more fixed, like the number of pages in a printed book.
Okay, so our playlists are mutable and our books are immutable. How does this relate to Python objects?
Well, in Python, mutable objects, like lists and dictionaries, can be modified after they're created. So if you pass a mutable object to a function and the function changes it, those changes will affect the original object outside the function too.
Wait, really? So if I have a list of groceries and I pass it to a function that adds ice cream to the list, My original grocery list will actually get updated with ice cream.
Exactly. It's because both the original list variable and the function's parameter are pointing to the same list in memory. They're like two different labels on the same container.
Okay, I'm starting to see how this could be both powerful and potentially dangerous. What about immutable objects?
Immutable objects, like numbers and strings, can't be changed in place. If you try to modify an immutable object within a function, Python will actually create a brand new object with the modification. The original object remains untouched.
So if I pass the string hello to a function and tell it to change the h to a j, it wouldn't mess up my original hello.
Precisely. Instead, a new string jello would be created within the function's scope. This immutability helps ensure that data doesn't get accidentally corrupted, especially when multiple parts of a program are interacting with the same objects.
Immutability sounds like a good safety feature. Now, what about those mysterious namespaces? I've heard the term thrown around, but never fully grasped what it means.
Imagine you have a massive library with thousands of books. To keep things organized, you'd probably have different sections for fiction, nonfiction, history, science, and so on.
Right, libraries need organization, otherwise you'd never find anything.
Well, namespaces in Python are like those sections in a library. They're containers that hold variables. This helps to prevent naming conflicts. You can have a variable named count in one namespace and a completely different variable named count in another namespace without any confusion.
So it's like having separate rooms for variables. I could see how that would be helpful, especially in larger programs where you might have tons of variables float around.
Exactly. Now, each time you define a function in Python, you're essentially creating a new namespace. It's like setting up a dedicated workspace for that function's variables.
Okay, I'm picturing these little workspaces popping up whenever I call a function. But how does Python know where to find a variable if it can exist in different namespaces?
That's where the LGB rule comes in. Imagine it like a treasure hunt. When you use a variable name, Python goes on a search, following a specific order. Local, enclosing, global, built-in.
A treasure hunt for variables, I like it. So it starts locally, like in the function's own workspace?
Yes. If Python can't find the variable there, it expands its search to the enclosing namespace, which could be the namespace of a function that contains the current function.
So like if the variable isn't in the function's immediate workspace, it checks the surrounding room?
Exactly, and if it's still not found there, it goes to the global namespace, which is like the main library floor, holding variables accessible throughout the module. Finally, if all else fails, it checks the built-in namespace, which is like a special reference section containing predefined functions and constants.
Wow, that's a pretty thorough search process. Now, these namespaces, do they just hang around forever? What happens to them when a function finishes running?
That's a great question, and it leads us to the concept of context. Think of it like this. The global namespace is like a permanent exhibit in our library, always accessible. But a function's namespace is more like a temporary exhibition. It exists only while the function is running.
So as soon as the function wraps up, its little workspace is packed up and disappears. What happens to the variables inside?
They vanish too, unless they've been explicitly saved or returned. It's like returning the books to the main library after the exhibition ends.
That makes sense. Now, you mentioned something about interactive mode earlier. Does that behave differently when it comes to namespaces?
That's an astute observation. Interactive mode, the one you use in the Python shell, is interesting because it acts like a dynamic module. Every command you type is like adding a new exhibit to this module's namespace, which persists until you close the shell.
So it's like building our own temporary library as we experiment with code.
Precisely. It's one of the reasons why Python is so great for interactive exploration and data analysis. You can test snippets of code, define variables, and build up a mini program within that interactive session.
This whole namespace and context thing is starting to make a lot more sense now. But what about the objects themselves? We've created all these objects, stored them in different namespaces. But what happens to them when they're no longer needed?
That's where Python's garbage collector comes in, like a diligent librarian ensuring that no shelf space is wasted. It's responsible for cleaning up objects that are no longer referenced by any variables.
So it's like a cleanup crew for our code, making sure we don't have a bunch of unused objects cluttering up our memory. But hold on, what about that del command? Doesn't that delete objects?
Ah, that's a common misconception. The del command is more like removing a book's entry from the library catalog. It removes a variable name from a namespace, but it doesn't necessarily destroy the object itself.
So the book might still be on the shelf, but nobody can find it because its entry is gone.
Exactly. If that variable was the only reference to the object, then the garbage collector will eventually swing by and remove the uncatalogued object. Think of it as a two-step process. Del removes the reference, and the garbage collector handles the actual cleanup.
Okay, I'm finally wrapping my head around this. Del is for dereferencing, not deleting. But is Python's garbage collection always perfect? Are there ever times when we might need to intervene?
It's a remarkably efficient system. But there are situations, especially in large-scale applications where we might need to manage memory more explicitly. Python provides a GC module, which gives us some manual control over the garbage collector.
So it's like we can step in and help the librarian tidy up if things get out of hand. But it sounds like Python does a pretty good job on its own most of the time.
That's the beauty of it. Python strikes a balance between automatic management and giving us the tools to fine-tune things when needed.
This has been an eye-opening journey. We've gone from building Lego skyscrapers to exploring vast libraries. But before we get lost in the stacks, I have a burning question. Now that we know about mutability, namespaces, and even garbage collection, how do these concepts shape the structure of larger, more complex programs? Do they play a role in those design patterns and architectures you mentioned earlier?
That's a fantastic question, and it's the perfect segue into our next part, where we'll explore how these fundamental concepts lay the foundation for building robust and well-organized Python applications. Stay tuned.
Welcome back to our Python Odyssey. We've journeyed through the land of objects, navigated the treacherous waters of namespaces, and even encountered the elusive garbage collector.
It's been quite an adventure, but remember, these aren't just abstract concepts. They're the tools and principles that empower us to build amazing things with Python.
You left us with a tantalizing question at the end of the last part. Now that we've got a handle on these fundamental concepts, how do they actually influence the design and architecture of larger, more complex Python programs? I'm picturing a master architect, carefully considering mutability and namespaces as they draft the blueprints for a grand software project.
That's a great way to visualize it. Just as a well-designed city has distinct districts with specific purposes, well-structured Python programs leverage namespaces to organize code into modules and packages. Think of it as creating clear boundaries and hierarchies within your code base.
Okay, so namespaces help prevent those chaotic situations where variables with the same name collide and cause all sorts of mayhem.
Exactly. Imagine you're building a complex web application. You might have one module handling user authentication, another responsible for database interactions, and yet another dealing with the user interface. Each module gets its own namespace, so a variable named password in the authentication module won't clash with a variable named password in the database module.
It's like having separate compartments for different parts of the machinery, so they can work independently without interfering with each other.
Precisely. And scopes come into play as well. They act like the doors and access points within our code city, controlling which parts of the program can access certain variables.
So it's like having different security clearances within our code base. Some variables are top secret, accessible only to a select few, while others are more public.
That's a great analogy. Good software design is all about managing complexity and minimizing the potential for unintended consequences.
Now, you mentioned earlier that good software architecture also emphasizes modularity. How do those well-defined modules relate to these concepts we've been discussing?
Well, modularity is all about breaking down a large program into smaller, self-contained units, each responsible for a specific task. And guess what? Namespaces play a crucial role in defining those modules and keeping their internals neatly organized.
So it's like assembling a complex machine from prefabricated components, each with its own clearly defined function.
Precisely. And this is where Python's object-oriented nature shines. We can encapsulate data and behavior within objects, creating those reusable building blocks for our modules. Remember those Lego bricks? They're back.
It's all coming together now. We're using those Lego objects to construct entire cities of code, with well-defined districts, namespaces, secure access points, scopes, and prefabricated components modules. But what about memory management in these sprawling software metropolises? Does garbage collection still keep things tidy?
Absolutely. As our programs grow larger and more complex, memory management becomes even more critical. Python's automatic garbage collection keeps working diligently behind the scenes, preventing memory leaks and ensuring that unused objects are efficiently recycled.
But are there ever situations where even the most diligent garbage collector needs a little help?
There are. In performance-critical applications or when dealing with resource-intensive tasks, we might need to take more fine-grained control over memory management. Remember the GC module we mentioned earlier? It gives us the tools to tune the garbage collector's behavior or even implement our own memory management strategies.
So it's like having the option to hire a specialized waste management team if our city's regular garbage collection can't quite handle the load.
Exactly. Python provides a great balance between automatic memory management and giving us the flexibility to optimize things when needed.
Wow, this has been an incredible deep dive. We've gone from understanding the building blocks of Python to seeing how those blocks come together in the grand architecture of large-scale programs. I feel like I've not only gained knowledge, but also a whole new way of thinking about code.
Remember, the power of Python lies not just in its syntax, but in the underlying principles that guide its design. By mastering these concepts, you're not just learning a language, You're learning a way of thinking, a way of crafting elegant, efficient, and robust solutions to real-world problems.
So for anyone out there listening, remember, embrace the power of objects, navigate namespaces with confidence, and respect the role of the garbage collector.
And most importantly, never stop exploring, experimenting, and building amazing things with Python.
That's a wrap for this deep dive. Until next time, happy coding!